All right, so we're going to look at solutions to equations. In particular, we're going to look at solutions to trigonometric equations, and even more specific than that, we're going to look at reciprocal circular functions and how to solve those types of equations. Some of the prior knowledge that we're going to need for this is obviously need a pretty strong foundation in regular circular functions, and knowing how to solve those is going to be important for this, but also general solutions to trigonometric equations, which was covered in the methods 3 and 4 course. So then some of the key concepts we'll cover are general solutions to trig functions review. So we're going to review some of those ideas from the methods course. And then we're going to solve some of our own reciprocal trigonometric functions in this video as well. It's really just one extra step you need to include in your working out, because you just need to recognize that it's the reciprocal circular function and then just make the relevant algebraic manipulation. And then we're going to look at using identities to solve equations. And then we're going to look at analysis of functions, in particular, looking at how to find the maximum and minimum of certain functions. Given some facts or given a certain function, seeing if we can work out the maximum and the minimums those functions. So let's jump into it. Let's maybe review this general solutions, which again is covered in the methods course. So this part on the left here hopefully looks somewhat familiar. I know it looks confusing, but hopefully it's familiar in terms of how you find the general solutions. So if you've got some equation cos x equals a, the general solution is 2n pi plus or minus cosine inverse of that exact value a, right? Similarly for sine can be expressed in two different ways. It's 2n pi plus or minus pi inverse, or it's 2n plus 1 pi minus sine inverse of that exact value on the right-hand side there. And then we've obviously got tan. Tan's a little bit different, but the general solution for tan is n pi plus tan inverse of that angle. I suppose maybe what we could do is look at an example to hopefully sort of refresh your memory on some of those things. So if the question was something like solve the equation cos x equals 1/2 for x, we could solve that generally. Because it hasn't given us a domain, we need to be able to solve this generally. So we can use a general solution to say this. We know that general solution for a cosine is 2n pi plus or minus the cosine inverse of that angle. And we know a is 1/2. So basically, to sort of dissect this part, we're asking ourselves, for what cosine angle do we get 1/2 as the exact value? So this is where you need to know your exact values. But I think you would agree cosine of pi on 3 is equal to 1/2. So therefore, cosine inverse of 1/2 is equal to pi on 3. And so then that's what we've got here. Just sort of think to our unit circle for a moment. I'm just going to get rid of that for a second. If we just think about our unit circle, this angle here, from here to this point here, is pi on 3. And because remember, think of all stations to Camberwell, or CAST. You've got cosine being positive in these two quadrants. So you've got pi on 3, and then you've got this around here at this next one would be at 2 pi minus pi on 3. Alternatively, we could just say it's at negative pi on 3. So if we started here at 0 and come back pi on 3, we're at negative pi on 3. So you can see that all of our solutions, generally speaking, we're going to get solutions at the even multiples of n pi. So here, because it goes 0, 2 pi to here again, 4 pi, 6 pi, 8 pi. And then we add pi on 3 to that, or we subtract pi on 3 to that, and that will give us our general solutions. So we would say that our general solution is x equals 2n pi plus pi on 3, or x equals 2n pi minus pi on 3, where n is an integer. Okay, because remember that 2n pi is going to give us even multiples of pi, so it's going to get us back to here on our axes. Okay, and then just with that graph that I had before, I think you would agree if we were to sketch this should all work out, right? What we've got in green here is the cosine x graph, and then this black dashed line is at y equals 1/2. So I think you would agree that these points here, if I get them to come up with their... No, actually, it's not going to work like that. But I think you would agree that these points here, this first solution, this first time it hits it, would be at when n is 0. So this is going to be at pi on 3. And then the next one would be at when n is 1. So that would be 2 pi plus pi on 3, which is what, 7 pi on 3. So this one's at 7 pi on 3. This one's at pi on 3. This one's at negative pi on 3. This one would be at negative 7 pi on 3. And then you just keep playing that same game over and over for the rest of the cosine graph, and you get infinitely many solutions. So hopefully that's a bit of a refresher from the methods course. That's how you sort of find a general solution. What we want to do now is just apply the same logic, but to a reciprocal circular function. And that might look something like this. So you might get given a question that says something like, solve the equation cosecant of 3x minus pi on 4 equals negative 2 on root 2 for x between 0 and pi. So in this example, we've now got a reciprocal circular function. And so hopefully you can recall from previous videos that cosecant is 1 over the sine. So what we're going to do is we're going to say that this is going to imply, we just need to take the reciprocal, right? So the cosecant is 1 on sine. So if we flip both sides of the equation, I think you would agree we'd get sine of 3x minus pi on 4 equals negative root 2 on 2. So we've flipped the right-hand side and we've flipped the left-hand side. So now essentially we just have a problem like we had before where we just need to solve the equation. This time we've been given a domain though, so we're not looking for a general solution. We're looking for a specific solution, although we could find a general solution if we wanted to. In any case, let's find a solution to this. So we're going to let theta be 3x minus pi on 4. So we just sort of set a parameter theta to be equal to all this business in here. And then we're going to do this step of adjusting the domain. So we then need to take our domain, which is between 0 and pi, and then apply these transformations to it. So 3 times 0 is 0, minus pi on 4 is negative pi on 4. Okay, 3 times pi now is 3 pi, minus pi on 4 is 11 pi on 4. Okay, so we have this at the moment. We've got sine of theta, where theta goes between here and here, equals negative root 2 on 2. And then we find those solutions for sine theta. So I think you would agree that using your exact values or thinking about your exact values, sine of negative root 2 on 2 is in these two quadrants down here. And it's an angle of 45 degrees or pi on 4 radians. So if we start at our lower bound of our domain, we're going to start at negative pi on 4, which is down here. And that's going to actually be our first solution because that's negative 45 degrees. And that has an exact value of sine being negative root 2 on 2. So we're sort of starting here, and then we come around, keep moving around in a positive direction, anti-clockwise direction. We keep moving around here. We're going to hit another solution down here. And that solution is going to be at 4 pi on 4, which is pi, plus pi on 4, which is 5 pi on 4. So that's another solution there at 5 pi on 4. This solution around here is going to be at 8 pi on 4 minus pi on 4, which is 7 pi on 4. And then we can't keep going because 11 pi on 4 is over here somewhere, and we'd have to stop. We wouldn't catch this next solution here again. So these are our 3 solutions. And then, now these are 3 solutions for theta, we need to find the solutions for x. So you got 3x minus pi on 4 now. We're just substituting theta back in. Equals all this. Okay, add pi on 4 to both sides. So you get 0, 6 pi on 4, 8 pi on 4. Simplify. You get 0. 6 pi on 4 is just 3 pi on 2. 8 pi on 4 is just 2 pi. And then divide by 3. So you get 0 pi on 2, 2 pi on 3. And so those are your final answers there. What I'll do is I'll just quickly show you a graph of what that looks like. And so here we go. So we're over on Desmos now. And if we graph the cosecant of 3x minus pi on 4, and we wanted to know where does that equal negative 2 on root 2, we can see that we get a graph like this. We can see that it intersects there at x equals 0, x equals pi on 2, and x equals 2 pi on 3. So if we go back to what we had, we can see that that is the right answers that we got. So just to highlight again, you're solving these the same way as you're solving trigonometric, regular trigonometric equations, but it's just sort of a first step you have to do of sort of flipping both sides of the equation because it's a reciprocal circular function. Okay, let's have a look at something a little bit different. If we have a look here, we're looking now at using identities to solve equations. So if you got given a question like this, cosine of x equals sine of x on 2, we need to think about how we'd go about solving that. And one thing we'd need to do is we'd need to use some of the identities. Now, I'll put a link below for this identity, but I think hopefully you can recall that cosine of x is equal to 1 minus 2 sine squared of x on 2. I'm saying that as if I remember that that's the case. But I'll put a link below because I think I've explained that before, but it doesn't necessarily, not that intuitive to me anyway. Anyway, so then we have to exploit this use of this identity, and then we say it equals sine of x on 2. Okay. And then trickily enough, we realize that it's actually a quadratic. So if we just rearrange things a little bit, we've got a sine squared term, a sine term, and a constant term equaling 0. And yeah, we're going to do this between 0 and pi, for x on 2 between 0 and pi. So let a equal sine of x on 2, just like we did before, whenever we've got a quadratic within a trig function. But then a will go between, one sec. Apologies, I realized the question makes sense. We needed to say that we're trying to solve this for x between 0 and 2 pi. So, okay, so that should explain this last step here. So we're saying x goes between 0 and 2 pi. So x on 2 therefore goes between 0 and pi because we've sort of applied this x on 2 to those domain values. Okay, and then we're going to say, all right, a equals sine of x on 2, which is sort of recognizing that it's a quadratic. And then a goes between 0 and 1. Why? All right, now I can explain it properly. Okay, hopefully you can see why x on 2 has to go between 0 and pi because x goes between 0 and 2 pi, so x on 2 goes between 0 and pi. Okay, when we make this substitution of a for sine of x on 2, we need to realize that we've got restrictions on the value of a. Now, remember, x on 2 can go between 0 and pi, so that's an angle starting at 0 going around to pi. Remember, sine of x on 2 would have a range from +1 to -1. However, if the angles that you can take on are only from 0 to pi, then the range of that function can only be from 0 to 1. You've sort of cut off. Our sine graph goes like this, goes down, up and then down, but we've sort of cut off the second part of it because we're only going from 0 to pi. So a goes between 0 and 1, not between 0 and pi or whatever else you might think it goes between. When we make that substitution, we need to think about valid values for a. Okay, after doing that, hopefully that made some sense. You just make the substitution, 2a squared plus a minus 1 equals 0. Okay, factorize. So you get 2a minus 1 equals 0, a plus 1 equals 0. All right, you get a equals 1/2 or a equals -1. Okay, a equals -1 we need to recognize is outside this domain. It's outside the constraints we've placed on a. So thus a equals 1/2. And since a is between 0 and 1, and we have that sine of x on 2 equals 1/2. And then that's just solving a solution. It's just solving a trigonometric equation. So x on 2 equals pi on 6 or 5 pi on 6. So x equals pi on 3 or 5 pi on 3. So cos of x equals sine of x on 2 between 0 and 2 pi as those two solutions. And lo and behold, here they are, sine graph, cosine graph in black, cosine graph in red, pi on 3 and 5 pi on 3, which I believe is what we said. So that matches that. So very good. All right, let's have a look at the last thing we're going to look at, which is sort of maximum minimum problems. So now we're going to get these combinations of trig functions. And one thing we can think about is what are the maximum and minimum values. So let's imagine we've needed to find the maximum and minimum of cos squared 3x minus 4 cos 3x plus 5, and also 1 over that. Okay, the key insight we need to recall is that just your basic sine graph and your basic cos graph both go between -1 and +1 inclusive. And that should hopefully be yeah, reasonable prior knowledge there. So what we're going to do is if we look at this, if we wanted to know the maximum and minimum of this without obviously graphing it, what we could do is we could let a equal cos squared 3x. Not that, that's not right. It should be cos of 3x. And so you make that substitution. So you get cos of 3x, you get a squared minus 4a plus 5. All right, then the tricky part here, you need to recognize that you need to complete the square. So if you complete the square on that, you're going to get a minus 2 squared plus 1. And then you make that substitution of a back in. So you're going to get cos of 3x minus 2 all squared plus 1. And then this is where, from this stage, hopefully we can read off the maximum and minimum values of this first function, because cos of 3x we know goes between -1 and +1. So we know that this part here is either a maximum of 1 or a minimum of -1. So let's just start with it possibly being -1. So -1 minus 2 is -3. We square all that, so we get 9, and then we add 1. So the maximum value is 10. In fact, we need to compare it with the other value before we know it's a maximum. But it turns out in this case that is a maximum. The minimum, let's take the other extreme where this is 1. So we take 1 minus 2 is -1. Squared is +1. Plus 1 is 2. So this top function is actually what we've got in green here. And I think you can see that it does in fact have a maximum at 10. And so I can just show you that. There you go. The maximum value there it gets up to is 10. Okay, and the minimum, sure enough, the minimum there, the minimum y value, if we get it right, it won't let me do it, but I think you get the idea. The minimum y value is 2. There we go. Okay, similarly now in red, we can think about the reciprocal of that. Okay, once you know this first one, what you can do is you can just take 1 over those values. So if we look here, we can see that the maximum is 0.5. And sure enough, 1 divided by 2 is 0.5. So that gives us this value here as being the maximum of the reciprocal composite circular function. And similarly, we can see down here, if we go to the minimum, we can see the minimum is at 0.1, okay? 1 over 10 is 0.1. So 1 over the maximum is going to give us a minimum on this reciprocal graph. And 1 over the minimum will give us the maximum on the reciprocal graph. So hopefully that's making some sense. It's tricky to explain some of these things, but in any case, if you're finding this in any way useful, give us a thumbs up. Let me know how I can help. If you need any private tutoring, please reach out. So good luck, and I'll talk to you soon.